without further ado, I would like to introduce Dan Guido, our keynote speaker.
Hello. I'm just going to hold this. Hey everyone, so my name is Dan Guido, and I am going to get my slides up. Of course, I didn't wear my glasses, so I can't see shit. Okay. Hey, so I'm Dan Guido. I run a company called Trail of Bits. We're a software security research and development firm that focuses on low-level security, cryptographic security, blockchain security. We focus on problems where people have consequences when they fail. We're split into a couple different service lines. We do security research with the US government to improve the foundational state of, improve the foundational state of, is this working? Okay, I'll keep going. I can take it off. There we go. Hello. Now I'm good? All right, now I'm good. So we do security research with the US government because they pay us to work long-term on fundamental problems in the space. We also do security engineering, where people hire us to build software that helps them. And we do security assurance work, where people give us software and help identify security risks and weaknesses in it, and the plans they need to move them forward. So part of our business over the last few years has evolved around blockchain security. It has all the makings of a perfect business for Trail of Bits. It has a highly motivated group of people that know that there's a risk of loss. It's a novel technology area that very few people understand. And it has allowed us to apply some of the research that we've learned through working with the government and through doing our own work. So I want to take you on a little bit of a journey of what we've learned during that. So Ethereum, right? So Ethereum, if we just wanted to make sure all of us are on the same page, Ethereum allows you the ability to write smart contracts. They're little automated finance bots that receive transactions and manipulate a global state. It has kind of a reputation, right? These tiny programs that are evolved in consensus, they do tokens, they do credit default swaps, you can integrate them with browsers, but they're built with a version of JavaScript, but shitty. And the community itself is not so into security, right? So we've got a little quote down here. That's from a real project that got hacked, where they say on their public Trello, a month or so ago, I asked a team member to reach out for auditing, but we didn't really remember, so we just launched without it, and then we got hacked, and it never really popped into our awareness. We didn't choose not to audit, we just forgot, right? So like, that's kind of what you hear about. We actually have a whole presentation by another guy in the audience over here, Evan Sultanic, called The Anatomy of an Unsafe Programming Language, which just describes the depths of failure, really, of designing this language that most smart contracts are written in. Now, the whole thing is a shared global computer. So people have the ability to send inputs to contracts, which are little finance bots, that can run code that manipulates global state, like balances. So you can see every transaction that happens, and you can send input to any contract or an account. That's sort of what the blockchain is. It's programmed, so here's a preview of this language. It's a JavaScript-inspired high-level language. This is Solidity. It's the most popular one. There are others, but most of them are similar. And it compiles down to something called EVM, which is a native machine code for Ethereum, which itself is kind of wonky. But this is really where we find the source of most of the blockchain's problems. There's this consensus layer on layer 1, but where most stuff blows up, it's this. So you know, you'd say like, oh, it can't be that bad. Like there's probably, you know, it's bad, but it can't be any worse than other languages that people use. No, it's really, really that bad. So the compiler produces really bizarre code. So you don't even have good tools to work with the language. So here's a case where it tries to calculate 1 by taking the exponent up to like, 100 or 256 or whatever. Like this is just wasteful code that costs people money. In fact, probably hundreds of millions of dollars over the lifetime of the Ethereum blockchain. So it's just absurd. And then the one at the top over here, because you declared something as a var, where is it? Yeah, so I is 8 bits because it gets declared as a var instead of a specific type. So that means that's an infinite loop if foo has greater than 256 elements. It's just like stuff that's not exactly expected as a normal developer, and they've introduced as many sharp edges as you can possibly create. To really drive this point home, here are all the security issues that are possible inside of Solidity that have mostly been eliminated from any other modern language invented in the last 10 years, right? Like, null dereferences are exploitable conditions on Solidity. The memory at the 0 page stores the owner of a contract, and if you can dereference it and change it, you can steal people's money, right? That's what we're dealing with. So this is what you'd expect. You'd expect that it's full of easy bugs, which is, yeah, it is. Make this a little bit bigger. That analysis of these languages is really tricky. They're using custom machine code. The language doesn't really make any sense. And that confidence in these systems is probably impossible. It's a stack machine, so you need to do really complex binary translation. It's based on JavaScript, so it's not really amenable to analysis. And that's, I think, what most outsiders view of the field. But as somebody that actually works in it, the reality is much different. And I think this sometimes comes as a surprise. We find that our clients in the blockchain space come in with a higher degree of security assurance than any other field we work in. They usually come in the door with precise descriptions of security properties, of automated analyses of those with fuzzing, symbolic execution, abstract interpretation. They're actually using, they've been able to find vendors. The vendor space, like that I operate in, is competitive for symbolic execution as a service. There is not just one option to choose from, there are 5, right? So this is kind of what we want the software industry to look like. This is what I want other clients of mine to come in the door with. Because these people have somehow created these conditions by accident. What if there is a way that the rest of the software industry could create them on purpose? So a lot of times people would back out and they would say, well, the reason why this happened is because code is law, right? You need to be right the first time and there's no recourse if you hacked. That's false. I don't really think that's true. So first off, there are a lot of other industries out there that have a lot of money to lose. People are building self-driving cars. Apple has a device in 1 billion people's pockets around the globe that hold extraordinarily valuable information. There are other industries where consequences happen when you don't do security right, and there are other industries where billions more dollars have been invested into making sure they are. So regular software needs to be correct too. And it's not just like, it kind of blows my mind sometimes to think about it. Companies like Google will literally create their own programming languages in order to keep their code safe, which is just a massive undertaking that's unparalleled when you look across the aisle at the blockchain industry, which is usually just a bunch of people running with their heads cut off. They haven't even planned this, and somehow they've ended up in a situation where 90% of people writing smart contracts are using precisely defined software properties as well as abstract interpretation in their normal development. So I don't think this is it. Instead, what I would want to look at is this little trope about a dairy farmer. It's a physics joke. It's a trope about an old joke where a dairy farmer says he's trying to keep up with the agri-conglomerate down the road, and he asks a physicist for help, who comes back weeks later and says he has a solution, but it only works on spherical cows in a vacuum. That's how it is reading most papers from ACM CCSS for the first time. But Ethereum is weird because Ethereum and most blockchain platforms only support spherical cows. They only actually support these systems that all the research can actually apply to. So this is kind of where the rubber meets the road for ideas brought up in the academy, where it actually gets done by real software developers that maybe didn't even go to college, but it gets done on software that goes into production that people use. So all this software testing research and Ethereum, because it has an extremely limited runtime, allows us to apply a greater degree of rigor in software testing and fix all these issues with the compiler and the languages in post. So at this point, I want to just step back for a second and talk a little philosophically about what a program actually is. So we're using the same language. I kind of hand wave over a lot of stuff here, so like we can have a nerd fight about it later, but it's a keynote, so don't kill me. So imagine that a program is a state machine, and that you take some input, and it changes the way the program behaves. Changes some state variables, has some effects, maybe it stops, maybe it doesn't. What you get on the left here is that's what I consider the input space to look like, just a little 2D grid, and that red dot there is where we've decided to send in some input. And then it kind of pinballs around inside the state machine, it does some stuff, maybe it doesn't do some stuff, but like, that's kind of what I think of as a program in this very reductive sense right now. So if that's what you think is a program, then software security is two questions. It's what inputs cause bad behavior, and then two is, so that's on the input side, and then on the other half of it is, when is a state bad? So where in the state machine do I not want to be? So like an assert would tell you that you encountered something bad, but not the input that caused it, right? So let's just dig a little bit deeper into the solutions to number one, and we'll show you kind of how this process goes, like what I think we're doing in security. So you've got the starting position, unrestricted input. It's a really big input space. People are flinging input at it. Sometimes people fling input that's not allowed or expected. Sometimes it's a different type. It's a round dot in a square hole, whatever. Anything can kind of happen. You don't exactly know what's going on. So as security engineers, you have two options. You can restrict input, where you could type your language instead of dynamically type it. You could delete some code. You could privset. You could split out. Essentially just all these different strategies to reduce the input space. And then the other option is you could test the input. You could test it randomly. You could test it formally. You could test it a variety of different ways. So unit tests would be popping out one hole at a time. A fuzzer would probably get a bunch of random dots all over it, and then property tests would probably wipe out like a column or a row. Now, side note here, you might be asking, well, where do mitigations fit in here? So mitigations don't fix code, they just limit the impact of failure. We actually don't care about mitigations. Mitigations are kind of a distraction if we're trying to write secure software. So just no mitigations, don't like them. So the maturity process that people go through when they're trying to do this, when they try to progress through that maturity kind of pipeline and they do one of those two things, is obviously they start at phase 0, which is essentially I'm going to train everybody. I'm going to tell everybody that they just need to try harder, that maybe they should get better at their job and write less bugs. And that's kind of where people start, and that's where most people are, I think. Obviously, I don't think it works. Computers are computers. They're not something that the human brain is going to be able to wrap their head around completely. This is kind of avoiding the issue, and it doesn't really lead anywhere great. I think of it like, just have your existing programmers work harder in the same amount of time, and we'll magically fix all the bugs. Phase 2 is you might actually try to test some inputs. So you would, this is unit testing, right? It's considerably better than not testing your code of just saying, well, we've got training, but it still doesn't really work because developers don't know what they don't know. So you can see we've got some random testing here. Most things probably aren't tested, and programmers aren't going to have awareness of the entire input space. They're only going to know what they expect. So a lot of these are positive tests instead of negative tests, which is what you'd want for security testing. So let's see. Yeah, this is, I think, where a lot of the good shops are, if we talk about traditional software. Like, if you start a project, or actually, there are companies out there that hire for software engineers that will brag about having unit tests. They'll list it on the list of benefits for joining the company on their careers page. They're like, yeah, we have unit tests. You can trust us. We're good software developers, right? So this is kind of like where most things sort of are. Approximately the industry state of the art. If you can test things, you're doing amazing. You're in like the top 10%. And then some people get to phase 2, which is trying lots of input. You get to fuzzing. So everybody that uses one of these tools always says they're amazing. Nobody says, oh yeah, like I tried AFL and it kind of sucked. Like, no, what they do is they try AFL and then they go, our Lord and Savior AFL, right? Like, it is the best thing when a developer gets even 5 minutes of exposure to an automated software testing tool like a fuzzer. This is getting a lot of industry acceptance, and you can see it in the litany of papers that have come out of academia trying to optimize the way that fuzzers work. There are just like dozens and dozens of forks of AFL that use a slightly different generation strategy to be like 2% more efficient in the way that they find bugs. So you can see that it's kind of got some industry acceptance, but this is really the minority. The number of clients that I would get in non-blockchain, non-cryptographic software that use fuzzers that I can walk in the door to and they hand me a harness is like very, very low. Yeah, how do you know if somebody uses property tests? They'll tell you. And then what you really want to get to is you want to get to phase 3, which is testing all the input. And this is kind of a joke, right? Like, people think that this is just unreal in the software industry. They don't think this is realistic at all. It doesn't give you perfectly correct software, right? Like, who verifies the verifier? And you could not be verifying all the inputs because you didn't realize where the total space ended, right? That's where that little extra box is on the right. Because maybe there was stuff that you verified, but you forgot you could send an input some other backdoor way. But it's strictly better than doing nothing. It's strictly better than the step that came before it. And the industry doesn't really want to do it because they consider it hugely impractical. So yeah, to recap, like, this is where the industry is today. Pretty much everything that's developed, nothing is checked that it's correct. At level 1, you have people that brag about it on career sites. They say that they have unit tests and CI. And at level 2, even like the people that are doing fuzzing, so we have a wonderful paper from an employee, Artem Dynaberg. We resurrected the original fuzzer from the University of Washington. We found the original code, we got it to compile on modern Linux, we reran it against the targets that they ran it on in 1989, and it still finds bugs, right? So application of fuzzing across the industry is extremely variable. People just aren't taking advantage of this stuff, so obviously no one's going to make it to phase 3. So why is that? When you boil it down, it's that we don't create testable programs, but the tools that we write require them. So the tools only work on small code and data, and nothing in production is small. So for example, we have a symbolic execution tool called Manticore. It's written to run on real software, but it can't model real system calls, right? Because there are hundreds of them. So you wouldn't know, or the tool wouldn't know what to do with something like uname, right? But the nice thing about blockchain software is you have to make it testable. Regular software, extremely hard to make testable. So yeah, for instance, like, how many unit tests are just 2/3 of the code in the file creating some kind of contrived environment? It's indicative that software is not super testable, that you have to create all this state before you can even reach the conditions that you're trying to test. And then functions will have side effects that change how other functions operate. So you have this explosion of state that's impossible to navigate from a software testing perspective. One problem that I've seen is that there are really bad abstraction boundaries. So everybody kind of mixes all their logic together into a global mutable state. Usually it's a key value store. It's something that's object-oriented. They all want to have their logic share components, but they have one thing that does everything. And I think systemd is like the poster child for this, where nothing is pure, everything has side effects, everything has mutable state. You can't know what it does. All you can do is observe some behaviors that it has that might or might not happen later. It's part of the reason why it's infuriating is because when people report bugs, you can't track them down. So developers find out about great research 20 years after it happens. If you pull software apart into smaller pieces, it's a huge gain for testing, right? So we started in a good spot. We started with Unix, and then each program did one simple thing, and now somehow we've got systemd, right? So that was kind of backwards. So global mutable state really, I think, is the root of all evil in this case. Problem number 2 is software is not reproducible. So we kind of assume that code works like on our laptops. I can't tell you how many times at Trail of Bits we get code delivered from our clients that just, either it comes with like a 20-page PDF that was written by some person that's not on the development team who never expected someone to set up a testing environment besides that person ever in history. Builds are a mess, right? Like there's not exactly a great way to get a repeatable build out of most software development teams. And we outsource logic to a lot of unpredictable environments. Like there's a lot of, well, I can only reach this bug if I prime the network with a couple of packets first. I'm like, how am I supposed to find that when I test? How am I supposed to figure out that's a bug when I just read the code? And the answer is you can't, right? It's unpredictable because logic is in the environment. It's not just in the code you write. Yeah. And then 3 is the input space is huge. So programmers don't know what stuff changes the behavior of their program. Like you want things that are kind of referentially transparent. You want stuff that's if you evaluate f of x, then you always get y. But that's not really the case. Yeah, I mean, this sort of makes sense. There's a lot of stringly typed code. You get white spaces everywhere. So if you're in a dynamic language or if you're just trying to parse things around, you end up forgetting that white space is a thing inside of a string, and then that leads to a whole bunch of errors. You know, this is why null dereferences are a thing. People aren't using types as much as they probably should, although we're seeing kind of a resurgence of that. So we try at Trail of Bits to read papers, to apply research despite these problems. And we know that it's not really designed for real software because we have a ton of trouble trying to apply it outside of specific industries. And at best, most of that research that we review is optimized for core utils. We can use it on binls, right? But I can't use it on some guy's you know, multi-billion-dollar code base that we're being paid to audit. And fuzzers are really the most realistic, but they have their issues as well. A former employee did a systematic evaluation of fuzzers and academic research in them over a couple-year period from University of Maryland, a guy named Andrew Roof. We wrote a short summary of it for our blog called How to Spot Good Fuzzing Research, where a lot of people were claiming really important improvements in the field, but they hadn't actually run their fuzzers in a rigorous way against others, and they sort of cherry-picked results. So out of those 32 different fuzzing papers, there was really only one that kind of met the criteria that Andrew set out for actually provably being better than the last person that came along. So at the end of the day, we just don't know when code is safe, right? At the end of the day, because we can't test stuff and because we can't, because there's poor abstraction boundaries, because it's not reproducible, because it depends on global mutable state, we just don't know when code is correct. We can't provide any sort of rigorous formal assurance back to people that, hey, this code is doing what you expect it to do. So security reviews kind of just feel like a thing that you do every year. You get in your yearly cycle, you find some bugs, next year you find a few more, maybe some of the same ones, and you're not really making progress. What I want to do is I want to provide evidence that software is safe against a class of bugs. I want to make demonstrable progress. I want to be able to verify or assert to my boss that the code is safer today than it was yesterday. And with blockchain, we are able to do that. So with this as kind of the state of software, we can look at blockchain as an unfortunate glimpse into the future. It's so weird because it doesn't really support the obstacles that we've encountered in regular software. So what does winning look like? So the big question, given my physicist analogy before, is if brown cows make chocolate milk, do spherical cows make Dippin' Dots? And I think you'll find out they do. So first off, where are we different? So in smart contracts, every change is a transaction. There are a couple of properties that are really interesting about this. All this stuff costs you money to get larger. Code is tiny. It has almost no control flow because it costs money to get bigger. So the incentive that is really important for blockchain software, instead of code is law, is that it provides this downward pressure to make sure code remains small. So this is an example of a real function that you might review in a piece of blockchain software. We reverse engineered it with something called EtherSplay, which is a disassembler that we wrote for EVM code. And that does something that's important to a smart contract. That's the total size of that code. So the input size is really expensive. The code size is really expensive. You have to pay per instruction executed. And termination is necessary. So you can take that whole area of computer science that I wouldn't say wasted a whole bunch of time in college, but like there's a lot of time that you can just spend not thinking about stuff because the properties of the environment have abstracted it away. So the incentives here have produced code that is small and clear, with clear abstraction boundaries, because every transaction is a state change. And the transactions are atomic. The other thing that's nice is that all this stuff runs in completely homogeneous environments. So everyone uses the same blockchain. I don't need to worry about whether I've got the same version of the DLL that you do. I don't have to worry about whether I've primed my network interface with the right packets to reach a bug. I don't have to worry about whether I have the same patch level of Windows. I know that if you're on the blockchain, I'm on the blockchain, and we're running the same code. And when state updates, all these things are also small, right? When things happen on the blockchain, the transaction data is tiny, and the state variables that change are tiny. So approximate numbers for scale, they have like hundreds of bytes per transaction. This is not hugely complicated for us to very rigorously analyze. So we get manageable state spaces. And this isn't because there's superbly clever design, right? These are all constraints to get around the fact that distributed system stuff doesn't scale. So from a back of the envelope math perspective, they're in a really great place to do rigorous testing. One thing that you get is symbolic execution being the most common technique in the space, which is like mind-blowing, right? So EVM has a few dozen more instructions than brainfuck, right? But it's basically the same thing. You can write a symbolic executor for EVM in a long weekend, right? Maybe a 3-day weekend, but it's not exactly the most difficult language or most difficult virtual machine to specify. Where instead, if you were trying to write symbolic execution for like the move instruction, it's pretty much impossible on x86 because there's like 50 different variants of it. Now the neat part about this is that not only is it easy to write the symbolic executor, but it's also easy to run it. The developer experience for symbolic execution on a smart contract is basically /find bugs. And then you can paste that into a browser. There are certain places you can go where you can just dump some code into a browser, press execute, and it will find bugs for you. It'll find different edge cases. It'll tell you what transactions to hit them. And people do it. When we go to conferences, not like this one, when we go to blockchain conferences and we talk to developers and we tell them about things like Manticore, our EVM symbolic execution tool, we'll have people sit down in the audience and run it on their code, and 5 minutes later they'll have found a bug before the presentation even ends, right? This is worlds away from where the rest of software testing is. Fuzzing, also extraordinarily popular. So it's kind of like in the right environment, these good solutions can be the easy ones to use. So the hardest part about fuzzing is how do you execute the code, right? So working solutions usually just have sort of a virtual machine built into them. So the fuzzer will execute the code in its own virtual machine. And the hard part about this is just identifying the invariants that you want to test against. So so in a lot of ways, it's kind of odd because fuzzing on smart contracts in some ways is easier, but in some ways is harder. Like if you wanted to fuzz for x86 code, if you had a binary, you can look for crashes. You know when you've hit a bug because it crashes the code, right? But there's no such thing as a crash in a smart contract. You have to tell it what you're looking for. You have to tell it that, hey, the conditions when I end up with more money and you end up with less, that's the sort of thing that I'm looking for. And you have to program that knowledge into a fuzzer beforehand in order for it to find you what you would consider a bug. So that's like a hard part. So the execution is really easy, but you have to look for things that are application dependent. You can't just look for seg faults. And then there's static analysis, which is kind of like the same as ever. It's amenable to the simplest possible static analyzer. Solidity is amenable to the simplest possible static analyzer. You parse it into a set of expressions, and then you look at who writes to state variables. Like that's kind of what static analysis looks like here. The thing that takes the most time is just writing heuristics for that. So we have a tool called Slither, which is much more advanced than something that just parses into expressions. But the very first version of it, we just parsed stuff to an AST and recursed through it, running simple queries, and that kind of worked fine. Again, you can write a really simple static analyzer for some of these smart contract languages in a weekend. But obviously then, writing the heuristics takes a while. So big picture is that on the blockchain, code correctness works most places. The developer experience is trivial. Developers love the experience when they try it, and Solidity doesn't give you any help, but that's okay. So these tools are extraordinarily effective. Like at Trail of Bits, we created all these things from scratch. We wrote our own static analyzer, Slither. We wrote our own fuzzer, Echidna. We wrote our own symbolic executor, Manticore. And when we combined them, there was one point early in our history, probably back in 2017 when we just started doing this, where we had to keep a massive Google spreadsheet of all the bugs that we were finding and already deployed code. It's pretty easy. So most of the time, when developers encounter that sort of experience, they get jealous. They close Telegram, because that's what everybody in blockchain uses, and they run the tools during the presentation. They build their own spreadsheet. Now, what we get is, thankfully in 2022, is we get developers that have already run these things, and they come in to work at Trail of Bits, work with Trail of Bits, and we don't have the luxury of being able to do /find bugs. We actually have to work hard, and we have to specify new security properties, and we have to push the limits of those tools and review the architecture of them to make progress. We had Gemini come in with their GUSD stablecoin, and they basically had 99% coverage of symbolic execution tests across their entire code base. I have never had that happen for any other client in any other industry. And that was years ago. That was 2019. And the field has only gotten better since then. So this is the ideal body. So I'll skip over this a little bit. We have a talk this afternoon where we walk through some of the tools that we use and the process that we use to extract the most value from them, given by Nat over here. Nat, raise your hand. So I'll just give a short preview, but generally the approach that we take when we review software is we need to get it buildable. If you can't get software reproducible, then you can't adequately test it, and there's no way that we can prove that we've made progress in terms of finding bugs. So no matter if it's blockchain software or not blockchain software, we are going to instrument their existing build system, and we have tools that we've written to do that, like Blight, which enables us to run really neat analyses on like C and C++ code at scale. We'll forward port existing build systems so that we have support for features we care about, like ASAN, And then every once in a while, a client comes to us and we'll actually rewrite their whole build system with them. We'll like up-convert it to CMake like we did with Zoom. And that allows us to test from a huge library of sometimes proprietary knowledge that Trail of Bits has about where bugs are, because we've spent a ton of time building up that list of heuristics and know, and have encoded, rather, that knowledge into a repeatable tool. And then finally, if that doesn't really work, I do like semgrep because it doesn't require buildable source, although there's some obvious limitations, but it is a good tool that we rely on frequently when we don't have time to rewrite a whole build system in CMake. And then the process for software testing is, rather than just read code every day and try to pick out bugs by hand, it's specify properties, encode them in the tool, repeat and recycle. So that at the end of an engagement, instead of just getting a list of bugs, what you're getting is a list of invariants with programmatic tests. This is what we deliver for all of our blockchain clients. We give them programmatic tests that prove that certain conditions are either always true or false. Yeah, I'll skip over this. So where do we go from here? So a bright spot is that languages are actually getting better. Compilers are probably where the biggest security wins happen, and we are finally souring on dynamic types. So people are moving away, or people care about having pure functions that don't have a lot of side effects. They're moving away from imperative loops. They use maps. Package managers have a role to play. A lot more people are using virtual env or Docker, which again have limitations, but this is substantially better than where we started. I would like it if we could get to a place where everybody uses Nix, but we're working on it. And you can see this in the data, right? This is a survey from Stack Overflow from 2021, where they looked at the popularity of different languages on the platform, and pretty much everything on the most loved side, Rust, Clojure, TypeScript, Elixir, Julia, Python, Dart, Swift, Node, and Go are statically typed, and then the dreaded ones are not. So thank goodness that starts to restrict the input space of what's possible for programs that people write. So generally in 2022, developers love type-safe languages. We're getting reproducible environments. So Docker is good. It's not exactly reproducible on its own. You have to do some extra stuff. But build systems are sandboxing now. I don't have to work through just a custom virtual machine with a PDF from 1998 with instructions for how to build something. A lot of people are integrating with GitHub Actions, and they have things like Stack and Cargo that help automate a lot of these actions and repeatedly build software. And once you're able to do that, it's not just helpful to security, it's also helpful to QA, it's helpful to prod, it's helpful to everybody else. So this kind of force multiplier, it isn't even originating with security, but we're being dragged along with it to great effect. One thing that I see that's a really big potential that hasn't really come to fruition yet is WASM. So I think it brings spherical cows to general computing. There's a little tiny bit of undefined behavior with respect to floating point, but it generally has all the properties we like about Ethereum. It has a reproducible runtime with well-defined inputs, and it enforces small programs. So we really can test WASM programs a lot easier than we can test traditional software. So I think that this work is more important than ever, and venues like this are where we can set the direction. So I just want to put it out there that we are here to help. We try to use research. We fund research if people are working on cool ideas. We bring in interns, co-ops, PhDs, and postdocs to come work with Trail of Bits and try to push the envelope on what's possible in software testing. So if you're one of those people, you should contact me. And if you'd like to get a preview of our research, then you can show up at 1:30 to see Nat's talk, or you can check out our blog, our specific GitHub organization called Critic, where we have all of our tools that do the kinds of things I talked about in this presentation, and our publications page, where we have presentations like this one recorded and PDF'd that you can go browse through. So thank you for coming, and I hope you enjoy the rest of the day. I think I'll take questions at the bar. I think we're a little behind schedule, or maybe I got us back on schedule. Good. All right. Thank you.
Sorry. So as one of the organizers, we get a little privilege to do things, but also I run Unciphered, and we have gifts for every speaker who speak and complete, and also don't think it was terrible. No. But thank you, Dan. This is a gift from the company. I actually designed these lockpicks at my last company, Rift Recon. They are called the PPK. They're made out of titanium, full hide leather, and I think they're the best picks you can get, and they work great with suits and cocktail dresses. Thanks. Thank you. Thank you for your talk.
And if I get to see you in a cocktail dress at some point?
Me? Oh, all right.